So continuing with our problem solving, in the previous lecture we have solved two problems related to the virtual work. One more problem I'll solve in this class, and then we will work out the equation of motion in generalized coordinate system by the Gaya-Lambert's principle. Suppose the problem is you have an active machine, or you can say two blocks hanging over a pulley by fixed string. So it's M2 M1 So first of all, we will work out in Newton's method, then virtual work will apply. So in Newton's approach, this is M2G, this is tension, string is supposed to be massless, so the tension same in both ends of M1. Suppose this is accepting down, so M2G minus, suppose in equilibrium, no equation, no acceleration. If the equation in equilibrium, M2G minus 2 is 0, T minus M1G is 0. This gives you M1 is equal to M2. So this will get this. Now if in motion, this can be written as M2G minus T is M2A T minus M1G is equal to M1A. Solve this, you will get M2 minus M1G divided by M1 plus M2. So the expression is given by this. Now this is the Newton's approach. Now we work out in virtual work. Applying the virtual work. In the virtual work, we have sum over Fi dot delta Ri. This is equal to the total work done. With the equation, if the system is in equilibrium, this is 0. Or in case of motion, Fi minus rate of change of momentum times this place virtual work. This is the virtual work, or it's set 0. So using the approach of virtual work, suppose this virtual displacement, that the virtual displacement of this block is, suppose we have considered infinitesimal displacement delta R2 and delta R1. Now this can be, delta R1 can be resolved into two components along the vertical, delta R1 vertical, delta R1 horizontal, or XY you can say, okay, horizontal vertical, whatever you like, you can write horizontal vertical, or so it is delta R2 vertical and delta R2 horizontal. So our from M2G dot delta R2 plus T dot delta R2. So this is the applied here, plus or here M1G delta R 1 plus T dot delta R 1. This is the virtual work. Now delta R2 has two components, vertical and horizontal. So it will be M2G delta R2 horizontal plus M2G delta R2 vertical. Similarly, the dot product again. Dot product. Now here T delta R2 over horizontal plus T dot delta R2 vertical plus now this one M1G delta R1 horizontal M1G delta R1 vertical plus T delta R1 horizontal plus T delta R1 vertical. This is the total work done. Now this is the horizontal component and this is MG, means the horizontal component this and MG makes 90 degrees with each other. So the dot product of them will be 0. So this is 0. M2G delta RV in the same direction. So it's cos 0. Cos 0 will 1. So it is M2G delta R2V plus tension here T. Tension and displacement makes 90 degrees with each other. So the dot product will be 0. 0. Here it's vertical. Delta RV displacement tension is in direction. The angle between them is 180 degrees. So it is T delta R2V cos 180, or you can simply write here minus 1 plus M1G delta R1 horizontal. M1G is delta R1 horizontal displacement 90 degrees. So this is 0 plus M1G delta R, okay, parallel M1G delta R1V. So it is again horizontal component makes 90 degree, vertical 180 degree. So it's again plus 2T delta R1V cos 180, and this is the total work done. Now the constraint equation means delta R1V is equal to minus delta R2V, R2V and R1V, because they are connected by a string which is the length of string is fixed. So one of the constraints is that the blocks are hung by a string which is, the length of which is fixed. So it will be, if you take delta R2 here, and delta R1V will be minus of this. So it will be M2G delta R2V plus T. This is 180 degree, so it's again minus T delta R2V plus M1G delta R1V is minus delta R2, so it's better to write minus here. M1G delta R2V. It's again 180 means minus, so it is minus, but delta R1V written as, so it is minus as plus delta R2V is equal to the total work done. Now in equilibrium the total work done is 0. So total work done, so the system is in equilibrium. So it is this and this cancels out. This is M1G. This is equal to M1 is equal to M2. So the system will be in equilibrium only when M1 is equal to M2. This is easier, which we have solved in the same result we have got from Newton's law also. Now question of motion. So in equilibrium we got M2 minus M1 G delta R2V. This is equal to 0. Now, equation of motion is M2G minus MA2 . Now, instead of writing 2 and 1, because 2 and 1 are the same, delta R1V is equal to minus delta R2V, simply write as delta R. 2V 1 V equal to delta R. So simply written as delta R plus M1G minus MA1 delta R is equal to 0, because we are using the same F minus P dot. Applied force mean minus plus the reverse rate of change of momentum. So it's the rate of change of momentum is here MA2, here is MA1. For 1, 2, for 2, for M2, what M1 is. So it means M2G minus M2A2 plus M1G minus M1A1 is equal to 0. Now A2 is equal to minus A1 because they are connected by same string. The acceleration of this and this will be the magnitude of them will be same but in opposite direction. So that the magnitude is A. So it is A2 is also A and A1 is also A. So one of them write as M2G minus M2A2 plus M1G minus M1, and A1 is minus A1 is A2. So it is A2 with minus sign, plus sign is here, or some mistake. Oh, there's a mistake. is delta R2, this is delta R1, and delta R2 and delta R1 is equal to minus delta R. So it's minus, and this becomes, so it's minus here and plus here, and now here it's A2, so it's minus here. For FIPI delta I, M2 A2 delta R2. Now delta R2 and delta R1 are opposite, so it is minus sign comes here. It must be delta R1, but I am written delta R2 with minus sign here. So delta R2 is taken as a common, and that becomes 0. So it is M2 minus, it's okay, here it's 1, here it's minus. M2 minus M1 G, M1 plus M2. So it is A is M2 minus M1 G by M1 plus. So the same result which we have found from the Newton's approach, we got by this virtual work method also. Now use a equation of motion. In the nice coordinate. So we have the equation of motion, or it's called D'Alembert's principle. That is Fi minus is equal to 0. That's the A for applied force. This is A for applied force. So we can say that F I dot delta Ri. Now I am not writing A here, assuming that this is the applied force, is equal to P dot I delta R. Now we have to solve, this is the equation of motion. We have to write this equation in terms of generalized coordinates. So the first, what is, suppose R, and it represents expressed in generalized coordinate Q1, Q2, Q3 and minus K. So the virtual displacement delta Ri will be equal to delta Ri by delta Qj, delta Qj. I am taking here as delta Ri by delta T as 0, because the virtual displacement does not involve, we are discussing only the change in the coordinates only, not with the time. Since the virtual displacement involves, since the virtual displacements involves only change of coordinates. Involves the displacement of coordinates in the and not its variation with time. So we have delta I is equal to delta I by delta Qj delta Qj. Its summation over Qj j plus delta I by delta Q1 plus delta I by delta Q2 plus delta so on. So it's summation over. If we write summation or not, because from Einstein's summation convention we know that repeated indices are assumed to be summed over. So we have got this. Now virtual velocity. So virtual velocity. In terms of generalized coordinates. Delta I by delta Qj by delta T plus delta I by delta T. Okay, summation over J. Now if you take you differentiate this with respect to dq dot, so it is delta I by delta Q j dot. So this is delta Q j dot. So if you differentiate this, you will get only delta I by delta Q j. Need not write this. So I am writing this as, because we will use that relation, delta I by delta Q j dot as delta I by delta Q. Because there is no Q dot j term here, so this will differentiate will be 0. This is delta Q j dot. So if you shade this, you will get only this. Now we have on our the number principle, we have Fi dot delta I. So it is Fi, and delta I is delta I by delta Qj delta Qj, or you can simply write I k Fi delta I by delta Qj. So this can be assumed to be a generalized kind of force, and this is a displacement in generalized coordinate. So this is a generalized force, summation over the Fi delta I by delta Qj, and suppose this Qj called generalized force, and hence this becomes Qj dot delta. So this is generalized force and this is generalized coordinate. So on the left hand side, this force and displacement, and this is also a force but in generalized coordinate, and this is the generalized coordinate may not be displacement length. So the dimension of this Qj may not have the dimension of force, but the product will have the dimension of the work. Okay. So the first we have this one part we have found out that Fi dot delta I is equal to Qj dot delta Qj. Now the next part is Fi delta I. This we have found out. And this part is Fi dot delta I. So this we have to calculate. So now Pi dot delta I and Pi means Mi Ri double dot delta I. Pi dot means this can be written as Mi Ri dot. Now this delta Ri in terms of generalized product will be delta I by delta Qj delta Qj summation over j. Now suppose this as, keep it as equation number 1, or you could keep it as 1 here, 2 here, and this as 3 here. Now equation number d by dt of Mi Ri dot delta I by delta Qj. Take the differentiation of this term. So the differentiation, the first term and second term. So take the differentiation to the first term. Differentiation of this means Ri double dot delta I by plus Mi Ri dot differentiation of this, so it is d by dt of delta I by delta Qj. Or we can write Mi Ri double dot delta I by delta Qj summation over I. This minus this, so this will be d by dt Mi Ri dot delta I by delta Qj minus Mi Ri dot d by dt. You can exchange this, you can write this as d by delta Qj times dRi by dt. And dRi by dt means velocity. There lies velocity, so it will be r dot here. So instead of writing here, we can just simply write it as okay. First step, we write that this will be d by dt mi ri minus this dr by dt is dvi, dr by dt, this velocity. Everything's okay up to now. Now this dri by dqj, del qj, from 1 we can write that delta I dot by delta qj dot. Using equation 1, this will become mi ri dot delta I dot by delta qj dot. So this is dot appears here from equation 1 minus mi ri dot delta vi by j. Ri dot means vi, and this is dvi by okay. So plugging from this side. Okay. D by dt delta by delta qj dot. Take the summation inside. Let's take half mi vi square. If you take the differentiation of this, you will get the same thing. 2 vi dvi by dqj dot. So it's here. And minus of this. This can also be written as using the same delta by delta qj summation over I. This you have used. Again, half mi vi square. take this as d by dt. Kinetic energy half of d square. This again minus del by delta qj. Again, total kinetic energy. And on this side we were having pi dot delta I. This was. Now this whole thing was multiplied by, okay, sorry, delta qj also, because delta I was, this was written as pi and delta I by delta qj times delta qj. We have solved this as expression delta qj dot. So it is here. Now, equating Fi delta I is equal to Pi delta I, and Fi delta I is, we have found out as Qj delta Qj. Here we have this is summation over j, so it is summation over j d by dt delta t by delta qj dot minus delta by delta qj delta t, simply delta t. This is simply delta t. So it is delta t. So it means d by dt delta t by delta qj dot minus delta t by delta qj is equal to, and this is the Lagrangian equation of motion. This is the Lagrange's equation of motion. This is the generalized force, and the generalized force was given as by we have just removed this. Okay. We have a generalized force. Generalized force is Fi delta I by delta T. This was our generalized force. So on the right hand side we have the generalized force, which is given by this formula. And if the force is conservative, if the force is conservative, this can be derived from potential. So the Qj, which is Fi delta I by delta Qj, this can be derived from potential. It means this can be as, if this is the potential, so delta I by delta Qj. means this is minus summation over j. So it is delta, it will be simply delta vi by delta j, because delta I v means delta v by delta ri. So delta v by delta ri, delta ri, delta v by delta qj. So the force is, if the force is conservative, this equation becomes minus delta v by delta qj. So we will arrange this equation. This is again the equation of motion for the conservative force field force. Now you can write this in another manner. You can simply arrange this delta so it's summation over j, because the repeated interest is here qj. So it is delta t by delta qj dot minus delta t by delta qj is equal to minus delta v by delta qj. You can write that t minus v minus delta t minus v is equal to 0. Take delta v minus delta v minus delta x. So it's a plus here and minus sign second order, so it's minus here. You just simply write here, because this will delta v by delta qj dot will be 0, because v potential depends only on position, not on velocity. So just writing to make it similar, and let us call t minus v as by new symbol called L. This is called Lagrangian function. So it will be d by dt delta L by delta qj dot minus delta L by delta qj is equal to 0. So this is our equation of motion for conservative force field, and this is called Lagrange's equation of motion. Lagrange's equation of motion is nothing but the same D'Alembert's principle, or you can say the equation of motion, equation of in terms of generalized quantity. And we will, in the next classes, we will do some problems using this equation of motion. Okay, so, okay, thank you.